Really?
Yeah.
That's cool. What if you only have 2 boys like us and you're on a 3rd kid? It'd be
Same odds.
Same odds.
It's mostly, it's like after 4 then it starts to become a trend or something.
I mean,
No, you were hoping.
that means you have a dominant wife from the dominant.
The dominant wife.
Why? No. What?
Dominant Y chromosome.
Why from the?
Like even if I cough loud, nothing happens.
Mine's productive. It's really gross. So I've been like holding it in, and then as soon as there's an opportunity, it's like. It's like.
Yeah.
I hate that.
Oh yeah. How you laughing? It's like I'm a smoker.
It's like the dad vibe.
Yeah, but this is the progression. Like, did you get? Mine was extreme sore throat, for like 2 days, at least in the night, and then it went to runny nose with mild sore throat, a little bit of like headache in there, and then now the runny nose is dissipating, and now it's into a cough phase.
Yeah, that's how I am. Mine was sore throat, runny nose, then it was stuffy nose with cough, and now it's mostly cough.
Yeah, wow, I'm on the progression. It's funny how certain colds work certain ways, and this is that.
Yeah, because they're always.
They are different. I think they're different.
Yeah.
Sometimes I'll have the runny nose going.
I hate that. Sore throat's the worst in my opinion.
Apparently for Johnny it's the stuffy nose. Okay, you are breathing. No, I'm crying.
That's so true.
So. Okay, we're gonna go into 1.2, finding limits graphically and numerically. So pull out your graphing calculator, taters. A limit is as something is approaching something. Now, not all limits, as we discussed I think last year as well, not all limits are going to infinity. They may be going to a specific value. And we can find out what those values are when we go to when we can do it algebraically, we can do it graphically. So in this we have, if we were to do just a basic function, doing a limit for this one would hold a whole lot of value because it's a linear equation. We have no issue finding out what it's going to because you can just plug in, right? But we could state, just for the limit notation, if I have the limit as x is approaching 5, that's the notation, for our function, in this case, we could write x plus 3 or just write f of x, I'll write x plus 3. What is the limit of that? All we're asking is, what is it going to as x goes to 5? In this case, yeah, it's a specific value that comes out, it goes and it hits 8. It's like, it's on 8.
It's done.
Okay, it's done. So now if we throw a different one up there, let's say you have x squared plus 4 all over x minus 2, let's say. Now if I stated for this one, so this is a rational function. Why is it a rational function?
It has real numbers.
Good one.
That is an idea. What does rational mean? Rational is a real number, but specifically rational.
Oh, it's a fraction.
Fraction, and specifically has a variable in the fraction. So it would be called a rational equation, rational function. So if I said the rational, I guess x goes to 1, okay, for this function, is there anything unique about that, or can I just plug in 1? Plug in 1, right? No problem. You plug in 1, what do you get out? Negative 5. I feel good about negative 5. Okay, so you get out negative 5. It's no problem. So if you're going to 1, now what happens when we say as x approaches? What number do you think I'm going to put in there to create something different, to create a challenge for us?
Infinity.
We could do infinity. That would create a challenge, but I'm going to put a numerical value.
Fraction?
Not a fraction, but that could cause a little bit of a challenge because you're working with fractions.
What about pi?
Not pi, but you could put in pi, and you'd have to do like a
X equals limit of x is square root of x.
in 2. Why 2?
Because x cannot equal 2.
Yeah, x can't be 2. So, but our function is going to go towards 2, right? And so when we do this numerically, if we wanted to figure out what this is, we want to figure out, okay, as it's going to 2, what value am I going to get back out? Or I'm not when I plug in 2, because I can't plug 2 in. So you could do, in this case, you could do like a little chart, and the book has these charts like this, and it's like, okay, you plug in for x, and you output for f of x. And so what you would do is, you know that you're going to 2, but you know you can't plug in 2, it's undefined, but you can plug in values on either side that are really close to 2 and see what the trend is. So you could plug in 1.9, 1.99, you could plug in 2.01, and then, you know, whatever you have here, 2.11 maybe.
Why not? X can't go past 2.1.
Why not?
Well, because you said limit of x is x to 2. You literally made this up yourself.
I didn't make up the problem. But
No, its limit is x arrow 2. That means it can't go past.
oh
2.
no, but I see what you're saying. As it goes to 2, it's not saying it can only come from the left-hand side. It's coming towards 2 from either side. Now there is a notation that we worked on last year, if you recall. If I want to state that x can only go to 2 from the left-hand side, do you remember that? We put a 2 negative. And if we wanted it going from the right-hand side, we put a 2 positive.
Interesting.
Yes. But if it's just 2, we're referring to it coming from the left and the right. So in this case, this would be a numerical approach, and you just have to plug in values. Now, the book, if I forget to tell you on the homework, I think they have like you plug in 5 values on the left, 5 values on the right, and you have a bunch of outputs. I don't actually want you doing that many values because I think we understand the concept of when you're plugging in values, you're looking for the trend of what it goes towards. So I don't need you plugging in 5 values on the left, 5 values on the right, and then analyzing it. Okay, probably plug in 1 to 2 values on each side. On the test, I'll probably have the same thing, maybe 1 value on each side to get to expedite the process. But if you were to formally do this with inductive reasoning, okay, would it really be necessary to like, hey, I've plugged in 5 values on the left, 5 values on the right. This really helps me understand that it's going towards this value. That would be the correct approach, right? Because if you only plug in 1 value on each side, are you sure? Well, not as sure as if you plug in 5 values on the left or whatever. So what do we, Riley's doing the math, what did you end up with? I don't have an answer.
No, I don't know. So when you plug in, if it's like the limit is 2 and you plug in 2, is it 0 or is it no solution?
Well, it's no solution, it's undefined.
So say if like the limit was 1 and you plugged in 1, it'd still be undefined.
No, here, the limit as x goes to 1, you get out -5. It's specific.
What does the limit even mean then?
It means as it's approaching that value, going to the value. But when you get into something like this, okay, and we can't just plug in the value to see what the output is, but it's going infinitely close to it. So in this case, you can't plug in 2, but you can say the limit is something. So what did you plug it in, Riley?
Yeah. 1.9 is negative 76.1. 1 or negative 1. Oh wait. Oh wait. I didn't put negatives. Oops. Okay, well, positive answers are 2.01 is 804.01. And then 2.1 is 84.1.
84?
Yeah.
And this is 804?
Yeah.
And then 1.99 was
negative 1.99. And 1.9 is -2.
-2 something. But then when you plug in 2.01, you're getting out 804.
Yes.
Okay. So what that tells us in this case, looking at that, is it going towards one specific value? No, because here it's going towards, you plug in 1.99 and you get out negative 1.99. Okay, I'm not disagreeing. And then here you're going to have something really large. So what that's telling you, it's actually the graph is not going towards a specific value. So that would be where there isn't a limit. It's not going to one specific value. But if we did another example here, a different function, I can create one for us that I think will get out one. Let's say I just mix it up slightly, x squared minus 4 over x minus 2. What is the limit as x approaches 2 for this? And then let's do of f of x, so our function. And then let's just do our chart, but let's just do it at 1.99 and then 2.01. We'll just do those two values. So Tate, why don't you do 2.01, plug that in. Riley, why don't you plug in 1.99. So then Tate, your 2.01, just going in for x, top and bottom, Riley's doing 1.99. 3.99, and then when Tate plugs in 2.01,
It's like 4.
Yeah, 4.01.
4.01. So looking at that, what would it tell you it's going to?
Basically infinity. It's not like a straight line.
No, what is it going towards? If you plug in 1.99, you get out 3.99. You plug in 2.01, you get out 4.01. It's going towards 4. Now on this, if you were to graph this, so go ahead and graph it. Graph x squared minus 4 over x minus 2, yeah?
Technically, you don't even have to do that thing because can't you just factor x squared minus 4?
Yeah, so this is what we call removable discontinuity, because you're going to be able to remove it by factoring and canceling it. But it's still discontinuous at 2. So when you go over 2 and then up 4, there will be an open circle. Now on your graph, when you go to graph this, your graph will not show an open circle. Your graph will just show a continuous line. But if you go to trace it, so if you go to trace this one,
I broke my calculator or something. I'm trying.
you broke it?
Yeah. So I'm here.
Yes, if you do a zoom box, will you be able to see?
No, you won't. Now with like Desmos or something, you might be able to see that value isn't showing up. But with this, so you end up with a linear looking equation, right? It's graphing it here. We'll show this on the video. You get a linear looking equation, even though it's an x squared minus 4 over x minus 2, as can be seen right there. But the reason why it's a linear looking equation is because, like Riley stated, when you factor that, DOS, x squared minus 4 turns into x minus 2x plus 2, you're just left with on the top x plus 2. So that would be your function. That's the look of it. However, when you go to trace, did you go to trace, Dave? Go to trace. It'd be funny if anybody watches this video outside of like Nick and they're like, who is this guy Tate? Like, Riley seems to be spot on, but who's this Tate guy?
Yeah.
When you go to trace, and I'm going to trace it at 2 and hit enter, you get nothing for y, even though it looks like a solid line through there. They just don't show the that it's not continuous through there. The calculator has an inability to do that for some reason. It just graphs it straight through. So when we go to graph this, my picture's a little bit off, but this one, you have this graph. Really what's happening is that, open circle. So what you're stating is, the limit is, as it goes towards 2, you get out 4. Because you're going to be infinitely close to 4, right?
Is the limit just the domain then?
The limit can be tied to the domain, but the limit is stating, you could state again, any limit. You could say the limit as x approaches 10 and see what value you get back out. So, and you can think about the limit. I talked about this, Tate, at one point, maybe last year, but if I was to stand here and I said I'm going to walk towards that wall, but all I'm going to do is I'm going to go half the distance that I went before. So the first step I go, I go halfway across the room, right? I stop, and now I'm going to go half the distance towards the wall.
Okay.
So then I go, right, half the distance. Then I'm going to cut that in half, right? Then I'm going to cut that in half. And then I'm going to cut that in half. And then I'm going to, right? The limit would be, where am I going towards? The limit would be the wall. Physically, I'm going to hit the wall. I'm going to run out of space. But mathematically, whatever hit the wall, if I'm only going half the distance. But I'm going to where? I'm going to be infinitely close to the wall. So the limit as you approach the wall, if you will, is the wall as you're walking half the distance every time. Yeah.
This is what the equation of the other one is at.
Right, there wouldn't be, for the,
X plus.
we said as x approaches 2 equals 4, and that's not 2. Yeah, because it would be a vertical asymptote. And so since it's rising at 2, right? Like where it's kind of hard to see there, I think, but at, it's like, I'm sorry, I messed that up. Like at over on 2, there's this line, they don't show it, but it's something like this, right? So at 2, there's this vertical line that it can't touch, but it's not going towards anything specific. One is going down, and then the other one's going up.
Yeah.
So it's not going towards the same value. So that would be the limit doesn't exist, correct?
Wait, so it's not a limit? Because they're not going.
In this case over here, they're going to different values. They weren't honing in on the same value. Here, they're going towards the same value, which was 4. So graphically, it would just be graphing it and seeing what it goes to. And then numerically, it's just the guess and check, if you will, like that. Now, we did have other ways that we did it algebraically for certain things, for as limits go to infinity, and we'll talk about some of that stuff later. Okay, go to page, because there's this thing called unbounded behavior. Unbounded, sounds like a parenting thing. When your child has unbounded behavior, what do you do? Unbounded behavior. That's funny. I was up at 2:30 this morning. My unbounded child.
Crying.
Daddy, I slept real well.
Sure you did.
I'm like stumbling through the kitchen.
Are those some dry tears I see coming down your face right now?
Dry tears. I don't know. Am I crying? I don't get. Is that a thing?
No. Saying you want to cry but you can't.
Yeah, I'm too tired to cry. So yeah, unbounded means it doesn't have a bound. It's going to infinity or negative infinity. So that's one of the things we talk about, which we just showed. There's no limit. It ceases to exist. The other places where limits fail to exist. So unbounded behavior, which is going back over to here, which we didn't. We just said the limit doesn't exist because it's not going to the same thing. One's going way up, the other's going down. The graph, I don't know if that's exactly what it looks like. You could graph it, rather than graph it, it goes down, one goes up, something like that. So it doesn't go to one value at 2, So that's where it fails to exist. So limits fail to exist in unbounded behavior. They also fail to exist when you have different right and left behavior. Okay, so in this, so unbounded, where they fail to exist, like going to infinity and negative infinity, up and then down, like that. Now they both actually could go up. You could have a graph going up and another graph going up, but they're just going to an infinity. It's not bounded. It's not going towards one value. It's going up to infinity. So it doesn't have to go up and down. So unbounded, and then the other one is where your left / right behavior don't match. Don't match. Now in this case, an easy one to look at would be I'll throw this up there and see if you remember. E. Yeah, it's the E. It's the what?
It's
like
from itself.
many limits on each integer.
Yeah, it's the greatest integer function,
Ah.
except you round down. So it's funny, it's called the greatest integer, but you're rounding down, which means it's kind of in my mind the least integer. So another like way you write this is f of x is equal to int on your calculator. Int x, you might see that. That means integer function x. If you want it to round up, it's understood that the greatest integer function rounds down. If you want it to round up, you would need to show it like this. You remember me talking last year, floor function, ceiling function. Ceiling rounds up, floor function rounds down. So, but otherwise, your calculator is going to understand it as a rounding down.
Do we have ceiling function?
You don't, but all you would have to do is add one. I think just add one to it, and it would take every value and round it up by one integer.
I thought that the two L's, I thought that'd make it like, if it was like, greater than 4.5 would go up if it was less.
No, it doesn't. It rounds it down. That's why it's the greatest integer. Everything rounds down. So if you plug in 4.1, it rounds it to 4. Plug in 4.6, it rounds it to 4. 4.999 rounds it to 4.
Is there a way to do it where it's like the classic way of rounding up, rounding down?
Oh, where you get to like 4.5?
It goes up, 4.4 goes down.
I don't know. It's a good question. You could. I'm sure if we took time to think about it. So here, if you plug in 0, you output 0. We'll call this 1. If you plug in 1, you don't output 0. You output 1. And then if you plug in 1.9,
You see, no one.
you still get out 1, but when you plug in 2, you actually then output 2, right? So what this states is, if I were to say, what is the limit as x approaches 2, let's say, of our greatest integer function, int x, and you went to do a numerical chart like this, right? You do a numerical chart, everything's going towards 2 for some reason.
Wouldn't that just be 1 or 2, depending on which side you come from?
Right, exactly. So you're raising the point we're going to make is if you go towards 2 from the left, so as you come from the left, you're always getting out 1. So this is going to be 1 because if you plug in 1.999999999, it rounds it down to 1. But then if you go the limit as x approaches 2 from the right, you're always going to be getting out 2. And so if those don't match, then it's not going to the same value, therefore the limit fails to exist. So you have unbounded behavior, you have left and right behavior doesn't match, don't match. So then that doesn't work. And then the third one is where you have oscillating. We don't see this as much. They give an example of sine of 1 over x, but it's where your graph, you know, it may come in, but then as it gets to like close to something, it just oscillates, and then maybe it goes off like this. Is that as you're coming towards any value where it's oscillating, it's going up and down, up and down, up and down. There's no, it doesn't hone in on one spot.
What would be like the line formula for that, right? Be something crazy, right?
The line formula?
Like, what would be the function for that?
Well, if one of the functions they use is like the limit as x approaches, I think their example was the limit as x approaches 0 of sine of 1 over x. And you know you can't plug in 0, right? So you'd be plugging in values leading up to 0. And then you know with sine is that it bounces, the sine wave bounces back and forth, back and forth.
Except at the end, because it just.
Well, that was, I just made that up. That doesn't necessarily match what this graph actually does. I was just trying to do the oscillating portion. So you could graph sine of 1 over x and then zoom in on it and see what's happening. And you'll see that it just keeps bouncing and bouncing and bouncing back and forth, back and forth.
I know, I was kind of thinking of like, remember that last year I visited the website how people would create art using like function line formulas?
Oh, the Desmos website?
Yeah, could you do that with any, could you create any line shape with a formula? Or is it?
Create any what?
Any like line shape? Like.
With some sort of formula?
Yeah, could I?
I don't know if you can have one formula to rule them all. It might have to be pieced together. You know, so like a piecewise function. So if you had a graph, it's like here's your line, and then it turns into a parabola, and then turns into a sine wave.
Yeah. How does that work?
It's not like, you know, I always like rail on all the, you know, YouTube videos that people waste their time on, and then I'm railing on myself for the videos I waste my time on. But I saw one like somebody was riding on a motorcycle that turned into a crocodile, which turned into a motorboat, that turned into a plane, and the person then they're like flying the plane. I saw it, and then it was like somebody's like my dreams after eating Taco Bell or something. I don't know what it was. But it was like that's exactly it. It's like it's just pure chaos. I was thinking about that because I'm like it goes from a line to a parabola to a sine wave, mathematical dream. So in this. In this, there isn't one equation, if you will. You can't write 5x plus 4x squared plus sine x. It's one equation to give you that. But what you could do is a piecewise function that says the first part up to this point is a line, this part to this part is a quadratic, this part on is a sine wave. Yeah, so that you could create a function, but it'd be made up of 3 different parts. I don't even know, are you even listening?
Yeah.
Hey, what's a piecewise function?
That's the crazy line things with the linear parabola sideways.
No, but like, what is it?
It's crazy.
That's crazy. Okay. There are, on page 51, they talk about common types of behavior associated with non-existence of a limit. So just things to make a note of. There's 3 different common types of behavior. One is if f of x approaches a different number from the right side of c than it approaches from the left side of c, which we just discussed. It approaches a different number, okay? It fails to exist. Increases or decreases without bound. So that was here. It was increasing to infinity and maybe negative infinity. We didn't quite get all the numbers exactly going, but it was increasing to infinity and possibly negative infinity. So there's no bound to it. And then the last one is it oscillates between 2 fixed values as it approaches that. Those would be 3 classic ones. Okay, the next phase is on page 52. They have this formal definition of a limit. Now, this is where I might end up giving you a slight disservice for if you were to take like a real rigorous Calc 2 course in college. Meaning, but you might take possibly with engineering, but meaning it depends on the professor, they might heavily emphasize formal definitions of things with the Greek letters and some of that stuff. Some of that stuff I gloss over and move fast because it isn't really necessary for our working calculus.
Okay.
I don't know if I'm right or wrong in that I feel okay with it and I haven't gotten any negative feedback from people. So I think we're okay with it, but that's what page 52 talks about is a formal definition of a limit. Now, one of the things in a limit is we have notation, just like we wrote up here, the limit as x approaches 2 of the greatest integer function x. Sure, that's the notation thing, but then you go down to the formal definition and it throws in some Greek letters, epsilon and what is that? Epsilon and we need
Why?
It's cool.
That's just chaos.
That's cool.
I can't even find the Greek letter for it. But anyways, epsilon is used in that they have this definition approach to it, kind of like a proof behind it. I don't end up focusing on that at all. If there is something that gets assigned, like in your homework, you're like, wait a second, I thought we weren't going to be talking about the epsilon stuff. We can address that when you get there. If you get started on 1.2 this weekend, you'll see that it says like 1 through 6 has charts given and they have 3 numbers on each side of the number you're looking at. Just do 1 on each side, don't do 3 and 3. Okay, because we get the concept, right? I think. So then another part it says create a table of values. When you create your own table, just pick 1 value on each side of the number. You don't need to create 3 numbers on each side of the number. If that also makes sense.
Okay.
Okay, and on the test, I maybe would have 2 values on each side max, but probably just 1 would make the most sense. You gotta take